Hi, I'm Keenan Casey for TutsPlus.com. In this lesson, we're going to be concluding our look at TCP by looking at how TCP provides all the services that it does in a very performant way. We've seen how TCP is a reliable, connectionful, safe protocol, provides a lot of services to applications that use it. Since TCP is so important, it's essential that it provide these services in a fast, efficient, performant manner, because performance matters when you're the workhorse of the internet. First, let's look at how TCP implements reliability in a performant way. We're going to look at this in two perspectives through pipelining and cumulative acknowledgement. The question that I want us to ask is, should we wait for an acknowledgement before sending the next packet? Let's consider both answers to the question. If we do wait, then we're going to have a scenario that looks like this. There'll be a sender and a receiver. The data will be sent over some period of time. The data will eventually arrive at the receiver, it'll be received, and an acknowledgement will be sent back. The acknowledgement should be a very short packet. The time that it takes to get from the sender to the receiver and back to the sender again is known as the round trip time. Now, what if the data transmission time is small compared to the round trip time? How will this affect the throughput, that is, the effective number of bits per second that can be transferred? Notice that in this scenario, for the majority of the time, the sender is just sitting around. It's not doing anything but waiting to get an acknowledgement back. When it does get the acknowledgement back, it will send the next data. This stop and wait protocol results in very poor bandwidth utilization when the round trip time is large compared to the transmission time. Notice that even though we have a potentially very fast link, the protocol design is restricting the usage of that speed. The takeaway from the stop and wait protocol is that it results in poor utilization. How can we improve this scenario? Well, what if we change our protocol and say, yes, you can send more than one data packet out before you receive an acknowledgement for it. This is known as a pipeline protocol. Let's consider another scenario using a pipeline protocol. In a pipeline protocol, we can send out multiple data packets before we get an acknowledgement for the first. In this scenario, as you see, we're going to send 3 data packets out back to back. As they're received, their acknowledgements will be sent back. And notice that all 3 data packets were sent in just a little bit more than the round trip time. Once we receive the acknowledgement for the first data packet, we can begin sending the next set of 3 data packets through the pipeline. Although this pipeline protocol complicates the implementation of the protocol, it drastically increases the utilization and therefore the effective throughput of the network. Now you see that in a little bit more than the round trip time, we've sent 3 pieces of data, whereas in this stop and wait protocol, we were only able to send 1 data packet. So pipeline protocols increase the bandwidth and the effective throughput of our protocol. Let's see how this would work in the case of TCP. Remember that TCP uses sequence numbers and acknowledgement numbers to keep up with the current state of the byte stream. We're also going to introduce a new variable that TCP has called send base. This is the last packet that the sender sent that has been acknowledged. So we're going to start here at 87. We're going to send a 3-digit string, so 3 bytes. The sequence number is 87. The acknowledgement number is 29. When we send this packet, the receiver is simply going to send back an empty acknowledgement. It doesn't have anything to send back, but it's going to send back an empty acknowledgement. And we're going to implement this in a stop and wait protocol. In this case, the acknowledgement that's sent back is going to be the sequence number 87 plus the length of this string that was received. That will be 90 altogether will be the acknowledgement number. That ACK for 90 will be sent back, and the send base will be updated to 90, and the next packet will be sent. If we send this 4-character string next, sequence number 90, acknowledgement 29, and the receiver will send back another empty packet that is an acknowledgement. That acknowledgement is going to be with an acknowledgement number of 94, which is the 90 sequence number plus the 4. This will continue, and our send base will be updated to 94. We'll send one more packet with just 1 character, 1 byte. That'll be sent, which will cause our next ACK to be 95. So this is a demonstration of what TCP's sequence and ACK numbers would look like if we used a stop and wait protocol. TCP doesn't do that. TCP is pipelined. Let's see what that looks like. In a pipeline version of TCP, which is accurate, the sender will send multiple packets before it receives any acknowledgements. So we send the first packet, the second packet, the third packet, and notice that send base is 87 the whole time. The send base number will not be updated until an acknowledgement is received. This is called a sliding window protocol, where the window size is the number of outstanding packets or the number of outstanding bytes in the pipeline. As packets are acknowledged, the window slides forward and more packets can be sent through the pipeline. TCP is going to restrict the number of unacknowledged packets that are transmitted in the current window, and that's determined by the receive window and the congestion window variables. What we see in this example is that 3 packets are sent and then 3 acknowledgments are sent back. As they're each sent back, the send base will be updated appropriately. So TCP uses this sliding window protocol to increase the effective throughput. That is, to overcome the really long round trip time with respect to the transmission speed of the network. So this pipeline protocol drastically improves the effective throughput of the protocol. One other mechanism that TCP uses to improve its performance is a cumulative ACK. Consider the case when a packet is successfully received but an acknowledgement is lost. And keep in mind, we're going to be in a pipelined scenario. The first packet is sent, and the acknowledgement for this, which should be ACK 90, is sent back but lost. From the sender side, it looks like that packet was never received, so it will continue sending packets in the pipeline. The next packet is this TUTS, which is a length 4. It gets sent, and then the receiver acknowledges it. In this case, the receiver is going to acknowledge the last byte that it correctly received in the sequence. In this case, that's 94. It received the 3 and the 4. So now this acknowledgement 94 is sent, and even though the sender never received the lost acknowledgement, it can infer that the receiver did in fact receive that data packet because this acknowledgement 94 cumulatively acknowledges that. So now the send base will be updated to 94 and the next packet will be sent. The sliding window will move forward. Essentially, ACK numbers say, I've successfully received every byte up to this number. So if a sender receives an acknowledgement, it can update send base to that byte, even if it hasn't received an acknowledgement for every other segment that had been sent in the pipeline. Secondly, let's consider how TCP's connectionful aspects are performing. How can we speed up the TCP handshaking process? Remember, the TCP handshake involves this 3-way exchange where the client sends a send packet to the server sends a send ACK back, and then the client sends an acknowledgement packet to finish the setup of that connection. The neat thing about TCP is it's going to reuse that acknowledgement as a data packet as well. So this acknowledgement packet, even though it's part of the connection setup process, can also hold real data. So in effect, it's almost a 2.5-way handshake, we might say. So this is one way that TCP's connection setup process is performing. The third way I'd like to look at this is how are TCP's safety mechanisms performing. And we're going to look at that in 2 ways, slow start and fast recovery, 2 things that are tightly bound together. The specific question that we're asking is, how can we efficiently recover from congestion throttling? Remember that at a loss event, TCP's congestion control algorithm severely restricts the transmission speeds. This aggressive reduction will negatively affect performance in terms of throughput. How can we detect low levels of congestion and respond less aggressively? And how can we efficiently recover from these low levels of congestion? TCP has 2 variables to help implement its congestion control algorithm. The first is the congestion window variable. The congestion window variable is basically the number of bytes that can currently be sent out in the pipeline due to the congestion level of the network. It's an estimate of how fast TCP can safely send data without congesting the network. The other variable is the slow start threshold. The slow start threshold is a number that represents the speed at which TCP will stop aggressively increasing its send speed and more conservatively increase its transmission speed. There are 3 modes of TCP's congestion control algorithm. The first is called slow start. It's triggered by a timeout. And when a timeout happens, the slow start threshold is set equal to the current congestion window divided by 2. The congestion window is set to 1. Notice that this is a very severe, aggressive reduction. When a sender is in slow start, however, it increases the congestion window in an exponential way. It doubles it. The second mode of TCP congestion control is called congestion avoidance. And this is sort of normal operation mode. It's triggered when acknowledgments are received, that is, when the congestion window is greater than the threshold that we found. In this case, the congestion window increases linearly. It increases by 1 each time that an ACK is received. The third mode is called fast recovery. Fast recovery is triggered when an acknowledgment that's a duplicate is received 3 times. So we receive the same duplicate acknowledgment 3 times. In that case, the slow start threshold is set to half of the congestion window, and then the congestion window is set to about that same value, half of its current value. Fast recovery is really a less aggressive way of responding to congestion because some of the packets are getting through since the acknowledgments came back. When we're in fast recovery, the sender will increase the congestion window linearly. Now let's see how the sender transitions between these different modes. The sender will start in slow start, which is very aggressive. This will ramp up speeds until the congestion window exceeds the slow start threshold. When the congestion window exceeds the slow start threshold, the congestion avoidance mode will start. This is a more conservative mode where the window grows very slowly. We increase by 1. If there's a timeout event, we'll go back to slow start. If we're in congestion avoidance and 3 duplicate acknowledgments are received, then we enter the fast recovery mode. In this case, the behavior is much more moderate. Whenever we receive a new acknowledgment, however, we'll go back to congestion avoidance, the kind of normal mode. If we're in fast recovery and there's a timeout, we'll go back to slow start and aggressively cut the congestion window. And if there are 3 duplicate acknowledgments, we will go from slow start to fast recovery. To sum up, TCP uses the following performance mechanisms in its reliability, connection setup, and congestion control. TCP implements pipelining and cumulative ACKs to implement reliability. TCP allows data to be in the handshaking acknowledgement as part of the 3-way handshake in the connection setup. And thirdly, TCP uses slow start and fast recovery to improve the performance of the congestion control algorithm. The main question we've considered is, how does TCP provide a reliable and safe connection without sacrificing performance? How does it do it all without sacrificing performance? First of all, TCP uses pipelining to increase bandwidth utilization. Secondly, TCP uses cumulative ACKs to help improve the efficiency. Thirdly, TCP allows the data to be on the ACK after the connection setup. Fourthly, the fast recovery and slow start algorithms improve the performance of TCP's congestion control algorithm by reducing the aggressiveness of the congestion control when appropriate, and thereby we increase the throughput. TCP is a very important protocol, and there's a lot that could be said about it. The main thing I wanted to get across in this lesson is that TCP is all about performance. It's so widely utilized, performance is essential, and there's a lot of work that's gone in to making it perform quickly and efficiently. I'm Keenan Casey for TutsPlus.com. Thank you for watching.